another capacitor leakage tester. This is the documentation of the experience of a hobby project, made with the hope that it could be helpful to others. However, these videos are not intended as tutorials. They only show the development of a personal practice, which may or may not be a good one. Therefore, if you are following along, you are doing so at your own risk. A very simple but effective capacitor leakage tester was published in June 2020 in the YouTube channel Restore Old Radios, and another project, derived from the one just mentioned, was published in October 2020 in the channel Tom Tech Test 8042. The two projects are very close, differing mostly by the presence of one or two transistors in a Darlington configuration for the purpose of multiplying the gain. Basically, if the device under test is traversed by a current, that current is amplified, allowing the LED to become bright. The resistor R1 is meant to prevent the destruction of the transistor in case of a short circuit on the DUT. R2 is meant to limit the maximum current traversing the LED. R3 is meant to be tailored so that the LED becomes bright only at a certain threshold of current, which would allow to control indirectly the minimal threshold of current that would be perceivable from the DUT. It would be meaningful to obtain a maximum sensitivity of about 2 gigaohms, because more than that would be impractical, due to the electrical noise in which we all are constantly submerged. The plan is to develop a variant of the projects mentioned in the previous section, adding also a millimeter together with the LED, but only a 2 amps meter is available. Therefore, it is opened with the intention of changing the internal shunt resistor. The shunt resistor is a wire and the resistance is not known. It is necessary to use a milliometer to measure it. The value is between 30 and 40 milliohms. Let's assume that that is exactly 35 milliohms. It is important to know what would be the voltage differential in the presence of the maximum current that the meter was supposed to measure. 35 milliohms multiplied by 2 amps gives 70 millivolts. Assuming for convenience that the coil of the meter has only a negligible resistance, 70 millivolts divided by the maximum current that the meter should measure at the end of its scale, 1 milliamp, the new shunt resistor should be of 70 ohms. But in practice, only a 68 ohm resistor is available, and therefore that is installed. Before proceeding, the meter is shorted temporarily because it would be sensitive to electrostatic discharge when the shunt is removed. The new shunt resistor is installed, but the one that is visible in this clip is not yet the final one of 68 ohms. The meter is tested, but as already mentioned, the shunt resistor is changed to 68 ohms off camera. Then the meter is reassembled. In an early version of the project, some tests are made for determining the additional shunt resistor to add in parallel to the meter, so that it can reach the end of the scale with the maximum current that could traverse the LED. This is the initial schematic diagram of this project, derived from the experience of Restore Old Radios in Tomtec Test 8042. In this case, the LED does not have a resistor in parallel, and it is meant to become bright whenever that is possible. In series with the LED, there is the millimeter adapted in the previous section, which has in parallel an additional shunt resistor chosen for obtaining the maximum deflection in case the DUT were a short circuit. 3 transistors instead of 2 are connected together to get the maximum current through LED and meter as soon as possible. Between the base of the first transistor and ground, a small capacitor is meant to absorb noise that would result in false leakage detections. The DUT is connected between the positive line, which is the elected ground of the circuit, and the base of the transistor, through resistor R3, which is meant to protect the transistor from a shorting DUT and from unexpected voltage potentials across the DUT. In case the DUT were polarized, the positive side should be connected to the elected ground. Round the DUT there is a switch that is meant to discharge it through the resistor R1 or to charge it through the network composed by the diodes D1, D2, and the resistor R2. Charging the capacitor under test would bring its voltage just below the point in which the base of the first transistor would become conductive. When the same switch is put in the middle position, open, if the capacitor has a leakage it would soon discharge and become visible by the transistor base. Here are the early tests with a breadboard starting with a series of resistors making in total about 110 megaohms. This is a new ceramic capacitor of 100 nanofarads rated for 1000 volts. The capacitor must be charged, and then one has to wait and see if the LED turns on. The capacitor can be disconnected and reconnected, but as long as it keeps the charge, the LED remains dark. Please notice that when the capacitor is disconnected, the LED is bright, sensing electrical noise. In other words, the capacitor under test is necessary to silence the electrical noise, and, for the same reason, low capacitance values could lead to false leakage reading. However, this aspect will be clarified only later during this experimental process. This is a very bad paper capacitor. It is charged a few times, but every time very soon the LED becomes bright, showing that the capacitor is not capable of keeping the charge. This is an old mica capacitor with a very low value which seems to be faulty, but it will be clarified later that it has no perceivable leakage and the tester is only showing electrical noise. This is an old electrolytic capacitor that seems to be still in very good condition. This is instead a new electrolytic capacitor, which seems to be bad, but is it? This type of tester needs a shielded probe to connect the DUT. But in this configuration, the shield would be positive, which is unusual, and in case of polarized capacitors, that would lead to unnecessary mistakes. Therefore, the design is inverted using PNP transistor equivalents and turning all other polarized components that are used in the circuit. Everything works exactly in the same way, except that the capacitors under test are now connected in a more sensible way. This is the way in which the project is built, using a prototype board and a common plastic electrical junction box, although a metal case would have been more appropriate. And here is how it is meant to be used, trying to test an old and very bad electrolytic capacitor. The tester is in the discharge position when the capacitor is connected. Then it is set to charge. Then the switch lever is moved to the middle position and the capacitor is tested. In this case, it is immediately reported as leaky. Unfortunately, this project is not working yet in the way that one would expect. For example, these are old, deteriorated microcapacitors, but only one of the entire batch is properly leaky, while for the tester, almost all of them are. This clip shows how important the influence of the environment is. At this point it becomes apparent that only capacitors with values above 10 nanofarads could be reasonably tested because they dampen the electrical noise of the environment. Therefore, a little modification is necessary. A 100 nanofarads film capacitor is added in parallel with the DUT, making sure that the external foil is connected to the ground. And here is the last capacitor that was tested and seemed bad. Now it appears to be perfectly fine. However, please bear in mind that the additional capacitance in parallel with the DUT introduces a delay in a possible leakage reading. It is important to understand some math behind the testing process, and for this purpose, the original NPN design is used as a reference because it is usually easier to read in this way, and also the last added capacitor C2 is ignored for simplicity. Assuming that everything goes like in a theoretical world, considering that there are 3 transistors in a Darlington configuration, the base of the first transistor would become conductive only at about 1.875 volts compared to the 0-volt line. Assuming that the battery supplies exactly 9 volts, that means that between the ground, which is positive, and the first base there would be a differential of 7.125 volts. Assuming that the 2 diodes 1 and 4007 drop only 0.625 volts each. When the capacitor under test is almost fully charged, the capacitor would hold a maximum differential of 7.75 volts. In other words, when the capacitor is fully charged, at the base of the transistor there would be missing 0.625 volts for becoming conductive. The invisible resistor that is in parallel with the capacitor under test will discharge this capacitor. and when it will have lost those 0.625 volts, it will be noticed by the transistor, and the LED will start to become bright. We start from the time constant of a capacitor, tau equal or multiplied by C, which represents the time in seconds that it would take a capacitor to discharge for about 63.2%. Then, it is possible to calculate the time that it takes to reach a certain level of discharge. For example, if the capacitor has a value of 1 microfarad, assuming a leakage of 1 gigohm, in about 84 seconds it would be detected. Assuming all the other values are fixed, if the value of the capacitor changes, the time changes linearly. 100 nanofarads would take 8.4 seconds. 10 nanofarads would take about 1 second. Assuming instead the capacitance fixed and the leakage resistance variable, if the leakage were of 2 gigaohms, it would take double the amount of time. In conclusion, heaping into account that this tester has an additional capacitance in parallel of 100 nanofarads if everything works as expected, and the purpose is to measure up to 2 gigaohms, and maybe even above that, one should always be very patient. With a proper insulation tester, the resistance at 1000 volts between two alligator clips pressed together is measured. It is about 1.5 gigaohms. Repeating the same experience with the tester of this project, knowing that there is inside a 100 nanofarads capacitor, the result is compatible with 2 gigaohms, which is reasonable considering that these alligator clips are newer and that the test is done only at 9 volts. The same experiment is repeated but without squeezing the alligator clips together. The tester is still capable of reading some weak current. The following clips show a comparison between two commercial meters and the tester of this restoration, verifying the insulation of these few capacitors. According to the meter, the insulation of this wax capacitor is higher than 2 gigaohms, but the next one disagrees. The last two capacitors show no perceivable leakage. Usually, if possible, in a restoration the electrolytic capacitors are replaced without too much concern. However, testing them could provide useful information. Moreover, also the new electrolytic capacitors should be tested before installing them. To test new electrolytic capacitors fairly, they should have been properly formed by the factory, but then also tested with a bench power supply close to the nominal voltage, controlling the maximum charging current. Assuming that the capacitors are able to complete the charge showing no perceivable absorption current under 1 milliamp, then they could be discharged and tested fairly. What is considered a forgivable leakage current for an electrolytic capacitor is calculated this way. The leak current is equal to the capacity multiplied by the voltage, all divided by 100, with a minimum of 3 microamps at the rated nominal voltage. Ignoring temporarily the minimum leakage current, the equivalent resistor in parallel, Rp, would have this value, 100 divided by the capacity. In practical terms, one should expect these parallel resistor values. Considering these values only, and still ignoring the minimal leakage at nominal voltage, this would be the time that would be necessary for showing leakage on the tester of this project, about 9 seconds. In addition, one should consider that at nominal voltage, a capacitor could leak at least 3 microamps. Testing at nominal voltage, the minimum parallel resistor value could be this. With these values, this capacitor tester would show almost all electrolytics as being very bad. Luckily, real capacitors perform much better, and it is only necessary to practice with reliable components to see what one should expect from others with similar specifications. Assuming that the tested capacitors have been prepared charging them before, close to their nominal voltage, and then discharged, a bad electrolytic capacitor would turn on the LED very bright very soon. However, capacitors rated 16 volts or below should be forgiven because they would have a significantly low physiological parallel resistance, due to the fact that they are tested close to their nominal voltage.